Welcome to day 2. We are starting with one of the most important questions. The question here is from the 2025 AP Chemistry FRQ exam. It covers the mass spectroscopy, and if you understand this one example, you understand the whole concept. Here is the question, but we will write it in an easier way for you to understand. In this problem, magnesium has 3 isotopes. We are told that magnesium 24 is the most common isotope of them at 79%. But there is a gap in the data for magnesium 25 and magnesium 26 isotopes. All we know is that they are approximately equal, and we are asked to find those missing abundance numbers. To solve this, we rely on one simple rule. The total abundance must always be 100%. If we subtract our 79%, we are left with 21% to split. Since they are equal, that's 10.5% for each of the remaining 2 isotopes. Now that the math is done, the real question is, why do these isotopes have different masses in the first place? Before looking, let's have a look at what we did again. 100% always the total minus 79%, that's equal to 21% remaining for 2 other isotopes. Divide the 21 by 2 since they are both similar. So I have 10.5% for every one of them. So I have to make one of the isotopes until 10. So I'll do this and it will reach 10.5%. And the other one is similar 10.5%. Since I'm asked to draw thick lines in the appropriate locations. So that will be almost equal to here. That's the actual paper from the 2025 exam. And the other one is similar to it, almost reaching to 10.5 or 10. Part 2 of the question asks for the structural difference. Part 2 of the question asks for the structural difference. Remember, the proton stays the same in all the isotopes. That's what makes it magnesium. The mass difference comes entirely from the neutrons. So magnesium isotope 24 has what? 24 minus 12 protons is 12 neutrons. Magnesium 25 isotope has 13 neutrons, and magnesium 26 has 14 neutrons. Simple, accurate, and full points on the FRQ. With the spectrometry handled, let's move on to our next major topic, stoichiometry and yield. The next question is from the same question number 1, but part B for the free response exam in AP Chemistry 2025. The particle diagram shown represents a magnesium ion, Mg2 plus in a beaker, a sodium ion, Na plus in another beaker, has a weaker attraction to water than the magnesium. Does explain this phenomenon using Coulomb's law and each of the following. Don't ignore the instructions from the examiner to explain using the Coulomb's law. I see too many students start explaining and they don't follow the instructions, clearly mentioning to follow the explanation using only Coulomb's law and each of the following. The relative charge of the ion, then the relative radii of the ion. So simply I have 2 ions that are dissolved in 2 different beakers. We are comparing how these ions attract water. Magnesium takes the lead here because of the charge. A 2 minus plus a 2 plus charge creates a much stronger Coulombic attraction to water than the sodium plus 1 charge. On the AP exam, always mention that a smaller charge results in a weaker Coulombic attraction forces. He has asked also to explain using the relative radii of the ions. So what we can say, we are going to say that the second factor is the distance. The sodium ions are larger than magnesium ions. This means that the distance between the sodium nucleus and the water molecule is greater. A distance increases, causing the attraction forces to decrease. Remember, smaller ions with higher charges are the strongest attraction in the solution. You can see in the drawing how the water is attracted to the sodium. I can see this is the water molecules attracted to the positive of the sodium, but because the sodium is having only +1, so the attraction is weaker, while magnesium has a +2, the attraction is stronger. The second factor is explaining, saying that sodium ions are larger. We know in the periodic table that as you go in the periodic table to the right, the size becomes smaller. So magnesium has smaller size. So just I'm making the magnesium very small to see how the bond will be smaller and stronger. And this one is big ion. The big ion will cause this distance between them to be big. So bigger distance means weaker attraction forces. Don't forget that F is directly proportional to the charges. That's why the attraction was stronger with the 2 plus, and it's inversely proportional with the radius squared. That's why the smaller one has a stronger attraction forces than the bigger one. So magnesium is smaller, it has more attraction. Whenever he asks to explain using the Coulomb attraction forces, we must say that forces of attraction directly proportional to charges and inversely proportional to radius squared. Again, focus, because this is what you are understanding from the question. Forces of attraction directly proportional to the charge of the first ion and the second ion. I have here only the cation, so this is +1. +1 is directly proportional to F, but it is weak. If it is +2 like in magnesium, it is stronger. Now let's look at the ions and their radius. So I have sodium is bigger than magnesium. Can you see how big is the sodium ion? But the magnesium is a smaller ion. That's why the distance between the sodium and the water is a big distance. That's why it's weak, because distance or the radius is inversely proportional to the forces. So here bigger distance means weaker attraction, while the distance here is small distance. That's why the attraction is stronger. So two things make the magnesium a better choice. In the day 2, we continue our mission. Right now is question 2 from the 2025 exam still. Combustion analysis is a very important skill. The College Board gives us a sample of ascorbic acid, that's vitamin C, and we have two critical numbers, 0.24 moles of carbon dioxide and 2.883 grams of water. They also give us a shortcut, the C to O ratio, which is 1:1. Let's use this data to build the empirical formula, but let's read the question first carefully. The student combusts a sample of the ascorbic acid to find out its chemical composition. The only product of the reaction are 0.2400 moles of carbon dioxide and 2.883 grams of H2O. Calculate the number of moles of H2O produced. The whole idea in the combustion analysis is that I have a compound organic molecule with C and H and O. I don't know its empirical formula. I burn it with oxygen in the combustion chamber. Then I collect the carbon dioxide and water produced, and I weigh both of them. From their weight, I can find their number of moles, and I can find the number of moles of carbon and hydrogen and oxygen. We will see how we'll do this. Then we'll come back to this graph again. So it's very simple. The number of moles of water will be found from the mass of water, mass over molar mass. And the number of moles of carbon dioxide will be found from the mass of carbon dioxide, mass over molar mass. Then I get number of moles of water, number of moles of carbon dioxide, and the trick is to find how many moles of hydrogen are there in the moles of water and how many moles of carbon are there in carbon dioxide. Why? Because if I know the ratio of the number of moles of carbon and the number of moles of hydrogen, and if I have oxygen also, I will tell you how we will get this. We can find the empirical formula of the compound. First, we need the moles of water. This is a classic gram to mole ratio. So number of moles of water is equal to this mass of water he has given, that's 2.883 grams, divided by the molar mass. Calculation using the periodic table, don't round the number, 18.02. We get exactly 0.1600 moles of water. What about the moles of carbon dioxide? He has given us the moles of carbon dioxide and said directly it is equal to 0.2400 mole of CO2. Remember oxygen? We said the number of moles of oxygen can be found here because he given us an information saying the ratio is 1 to 1, right? So the ratio is 1 to 1. So I have the same number of moles of carbon as carbon dioxide as oxygen. So let's see carbon and carbon dioxide relation. We know that if we balance any type of combustion reaction, the number of moles of carbon equal to the number of moles of carbon dioxide produced. So if you have one carbon, it will be one carbon dioxide. If you have CH4, you will get one carbon dioxide. If you have C2H4, you will have two carbons. So the ratio between carbon and carbon dioxide is always 1 to 1. So the ratio will be carbon to carbon dioxide is 1 to 1. So if you have carbon dioxide 0.2400, 0.2400, then that's equal to the number of moles of carbon also 0.2400. Why, Mr.? The ratio is the same. Ratio is the same, so it is always similar. Okay, and he said the number of moles of carbon and oxygen is the same. So the number of moles of oxygen is equal to 0.2400 moles. What about hydrogen? Hydrogen number of moles is not the same as water. Carbon number of moles is the same as carbon dioxide, but hydrogen number of moles is not the same as water. I cannot get it from the water directly. Same, I found the carbon from the carbon dioxide. When we burning a compound that has X moles of hydrogen, it forms H2O. So this means that the ratio actually is 1 to 2. If you have a compound that is C unknown and H unknown and O unknown, when you burn hydrogen, it does not bring hydrogen H, it burns into H2. So this has to be balanced into 2 to make this 2 and this 2, right? Similar. So the ratio actually is 2 to 1. So this means that whatever number of moles of water that you have, you must multiply it by 2 to get the number of moles of hydrogen. Why? Because the ratio, again, the ratio is 2 into 1. So if you have 0.1600 moles of H2O, this will give you the double 0.300 moles of H. So again, if you want to find C from CO2, it is the ratio, it is the same number, ratio is 1 to 1, but H from H2O, you must multiply it by 2, because the ratio is 2 hydrogens to 1 hydrogen here. So now I have the number of moles of oxygen and of hydrogen. Hydrogen is 0.3200, oxygen is 0.2400, carbon is the same, like he said, the ratio is 1 to 1. So all I need to find from the empirical formula is to divide them by the smallest value. Remember, if I'm finding the empirical formula, then carbon to hydrogen to oxygen moles, just divide them by the smallest value. This is 0.2400, this is 0.3200, and this is 0.2400. The smallest one of them is 0.2400. So divide all of them by 0.2400. This gives you 1, this gives you 1, and 0.3200 when divided by 0.2400, you get 1.3. Remember what we said about the ratios in the last video in day 1? We said that I cannot have 1.3 as my answer. I cannot have 1.3 as my answer. I must multiply it by 3. So it becomes a number like 4. It becomes 3.9 or almost 4. So if you multiply this one by 3, you have to multiply this by 3 also, and this one by 3. So it becomes 3, 3, 3, 4, 3. So the ratio is 3 carbons to 4 hydrogens to 3 oxygens, and this is my empirical formula.